In earlier sessions, I have talked about the different measures of quality, how you define quality, what are the ways we have to identify for different steel grades, what are the different criteria, which factors should be adhered to. Now, I will be talking about what is the importance of secondary refining in achieving the desired level of quality. How do you achieve it? What are the different ways we can conform to the application requirements of quality? One by one, I will go into all those issues. So, as I have told you earlier, secondary refining, that means ladle metallurgy, whatever you do in ladle for the final stages of quality improvement, that is very important. Secondary refining is a very important component of steel making. So, I will be going ahead with secondary refining. Now, let me talk about why in the primary stage itself we cannot achieve quality. What are the limitations of primary stage? Why secondary refining or ladle metallurgy is essential for achieving quality? So, by primary steel making, all of you know, it can be either basic oxygen furnace BOF, electric arc furnace EAF, or induction furnace. In induction furnace, you basically melt the constituents, the raw materials. You can do very little refining. So, let us go ahead. What are the limitations of primary stage? What are the limitations of BOF, EAF and induction furnace IF? The basic idea is the slag is rich in FeO. Why it is the slag is rich in FeO, iron oxide? Because all these are primary steel, all these primary steel making stages are basically, or in principle, they are oxidizing process. You are putting oxygen in the furnace. You want to oxidize some of the elements. In the process, the slag which is formed becomes very rich in iron oxide. It has lot of MnO, it has phosphorus oxide as well, because I have told you, because in the primary stage you can take care of phosphorus because of the oxidizing environment. So, because of the oxidation reactions, the slag is rich in iron oxide, is rich in manganese oxide, rich in phosphorus oxide. So, now what are the problems? This liquid steel, because of the oxidation process, is very rich in dissolved oxygen. That is why the slag is rich in iron oxide. The consequence is the liquid steel is rich in dissolved oxygen. It is as high as more than 500 ppm, it can go as high as 800 ppm. So, this is an issue to be thought about. That means, we have to bring down this oxygen in subsequent stages. In primary stage, liquid steel is very rich in dissolved oxygen, that is one important limitation. Moreover, since dissolved oxygen is very high, in this primary stage desulfurization is not very effective, because I have told you earlier, it will be very clear to you in subsequent stages that during desulfurization you need the liquid steel to have very small amount of dissolved oxygen, then only desulfurization will be very effective. So, since dissolved oxygen is very high in liquid steel in the primary stage, desulfurization is not at all effective. Then another important issue is the recovery of alloying elements poor and erratic. That means, when we are adding some ferroalloys, like we want to adjust manganese, we want to adjust silicon, we want to adjust some other alloying elements like chromium, maybe we want to adjust some other elements like even nickel. So, the recovery of the alloying elements are poor. That means, recovery is not poor. Whatever ferroalloys you are adding, whatever constituent of that particular alloying element is there in the ferroalloys or in the initial input materials, finally in the steel you get less than that. it is sometimes maybe as low as 70%, it may become 80%. So, it is recovery of the alloying element is less and it is erratic. Why it is? What do I mean by it is erratic? That means maybe one hit you can get a recovery of 70%, another hit you may get 90%. So, you really do not know when you are making a steel in primary steel making stage, what will be the recovery of the alloying elements. Why this is so? Again the culprit is more amount of dissolved oxygen in steel, more amount of iron oxide in slag. So, the alloying elements which we are adding, which we intend to add in the steel, they become oxidized and part of it goes to the slag. That is why the recovery is poor and erratic, it is also erratic. That means, it is not very well defined how much we will get in the final analysis. So, therefore, it is difficult to achieve the close chemistry ranges. Today, you should know that whatever alloy steel we are producing, whatever steel chemistry we are producing, the customer wants the chemistry should be very well defined, it should be very close. That means, there should not be a variation of the alloying elements from heat to heat. So, this is very difficult to achieve in the primary stage. Moreover, what is most important, the cleanliness level, good quality basically means the cleanliness level also should be high, the residual element should be less, the inclusion should be less, it should be a clean steel. So, that also is difficult to achieve, because you have very low amount of dissolved oxygen. So, total oxygen is high. Because of this, the possibility of inclusion generation will also be high during subsequent stages. If you want to cast a dissolved a steel which is having very high dissolved oxygen from the primary stage, you will have very high amount of inclusions, oxides. You will be having very high amount of sulfides, because the sulfur content is also very high. So, oxides and sulfides are more, that means the cleanliness level is poor. So, these are the difficulties at the end of the primary stage. So, this primary stage today is used only as a process for faster melting and preliminary refining. What do I mean by preliminary refining? Basically, we want to control to some extent carbon, to some extent sulfur, and of course, phosphorus in the primary stage. And the whole idea in principle is to get a base level of chemistry on which we can fine tune, which can be fine tuned in the subsequent secondary refining stages. So, I have talked about what are the limitations in primary stage. Now, what the secondary refining is supposed to do then? All of us know that steel, liquid steel from the primary stage, that means either from electric arc furnace or basic oxygen furnace or in induction furnace, this is tapped in a ladle. It has to be tapped in ladle, and then whatever treatments will be done, those will be done in the ladle. So, what do we want the secondary refining stages to do? We should be able to get very narrow ranges of alloying elements, which was not possible in primary stage. We should be able to get a homogeneous composition, that means there should not be a variation from one area of the liquid steel to the another. We should have improved cleanliness, very important requirement, as I am mentioning repeatedly. So, these are the important requirements. So, now if we get into the exact details, what are the desirable functions of secondary refining? What do we expect? What do we intend to do during these secondary stages? Let us go one by one. First and important is deoxidation, which is known as killing also. From practical point of view, some people call it killing of steel. So, deoxidation is necessary because the dissolved oxygen in liquid steel after primary steel making is very high, more than 500, 600 ppm. This must be brought down to very low level, otherwise it will be difficult to cast the material, otherwise the cleanliness level will be poor. So, this is the first and most important requirement, most important desirable function during secondary refining. Next is the carburization or decarburization. As I have told you, after primary steel making stage, we have a very base level of chemistry. Maybe the carbon content may be 0.5, maybe 0.6, maybe 0.4. Now, the final carbon level in the heat we want to process, which want to produce, the grade which want to produce may be having either lower carbon than this or higher carbon than this. If you want higher carbon than that, that means we have to carburize, we have to increase the carbon level. Again, if you want to decarburize the steel, that means we want a carbon level of say 0.2 or say 0.15 or say 0.25. So, that means we want to decarburize the liquid steel. So, this also can be done during secondary refining stages. Next, most important, or I must tell, one of the important requirements for having a good quality is desulfurization. That means the sulfur content of steel, liquid steel, has to be brought down at this stage. I have also told you that in most of the steel applications we need low sulfur, but there is one application requirement, specifically it is called machinable steel, where we want to have a very good machinability in steel. There intentionally we may add some sulfur in the steel to get good machinability, good chip formation during machining. So, there some sulfur addition may be necessary. That is of course a very one-off requirement, but most of the steel we want desulfurization, that means sulfur should be brought down. So, this can be done during secondary refining. Another important requirement is control of nitrogen and hydrogen. These two are gaseous elements. These two are present in liquid steel. Depending on the process of primary steel making, what are the process parameters? We may have some high amount of nitrogen and hydrogen in steel. So, this must be brought down for having good quality of steel. So, control of these gaseous elements, nitrogen and hydrogen, is possible in secondary refining stage. Then inclusion modification. As I have told you earlier, during deoxidation, what is happening is, I will come to this in greater detail subsequently, but just let me talk about it, talk about this, that inclusion formation during deoxidation, if you kill with aluminum, which is a very efficient deoxidant, what we are forming is alumina. These alumina inclusions are solid because the melting point of alumina is higher compared to the melting point of liquid steel. So, therefore, these are solid particles of alumina in steel after deoxidation. Similarly, we might have silica if we deoxidize with silicon. Now, particularly for alumina, which has a very high melting point, which is solid, if you want to modify the inclusions, that means if you want to change the shape of the inclusion, or we want to control the melting point of the inclusion and make it liquid during the time of steel making, what is the way out? We add something which will react with alumina and the melting point will come down. We know that CaO, when it combines with Al2O3, it is a possibility of bringing down the melting temperature through eutectic reaction. So, it is necessary to control the melting point of inclusions through injection of either Ca, that means calcium silicide, or Ca, that means calcium iron. The whole idea is to use calcium to modify the inclusion, to make it liquid, to make it spherical at the time of steel making. Now, another important requirement during secondary refining, desirable function you can tell, is control of liquid steel temperature. You know, when we are doing continuous casting or when we are doing even ingot casting, a typical temperature range is necessary. That means a particular superheat is necessary. Every steel composition has a liquidus temperature. Normally, the temperature of the liquid steel when it is taken to the casting bay, it is slightly more than the liquidus temperature. It is called the superheat. Now, we must cast at a particular range of superheat. It cannot be very high, then the structure will be bad, the solidification structure will be poor. It should not be very low, then there is a problem, there may be a interruption in casting, there may be premature solidification, and likewise there may be difficulties in during casting. So, control of liquid steel temperature is very important. So, these are the desirable functions in secondary refining: deoxidation or killing, carburization or decarburization, desulfurization mostly, control of nitrogen and hydrogen, injection of calcium, wear injection it is called, for inclusion modification, and then of course, control of liquid steel temperature. These are the desirable functions of secondary refining. Now, let me just go through what are the very common secondary refining processes which are used in modern steel making practices. First is called ladle furnace, which is known as LF. Another is inert gas purging in ladle. I have told you that from primary steel vessel, that means BOF or EAF, steel is tapped in ladle. Now, that ladle then is taken to different stages of refining, secondary refining. So, it may be taken inside a ladle furnace, or it may not be taken in a ladle furnace, but you may pass inert gas from the bottom, that is called inert gas purging in ladle. That means, the ladle should have facility for purging of inert gas from the bottom. It might be possible to blow inert gas from the top as well, but mostly ladles are having facilities of inert gas purging from the bottom. So, this is called IGP, inert gas purging. Then, as I have told you, the degassing, that means control of nitrogen and hydrogen in steel is very important. So, there might be a necessity of vacuum degassing. That means, you create some vacuum, you take the ladle inside a vacuum chamber, you create vacuum, and that will help in the degassing process. So, that may be VD, vacuum degassing. Now, we may have to require to increase the temperature. So, there may be a necessity of some arcing facility for increasing the temperature, because during the process of secondary refining, during the process of transporting the liquid steel from one vessel to another, and during transportation from one bay to another, temperature is coming down. So, there may be necessity of increasing the liquid steel temperature. So, some arcing may be necessary. So, vacuum arc degassing has the facility of vacuum as well as arcing. So, the temperature can be increased in vacuum itself. Then vacuum oxygen decarburizer, VOD, this is another important secondary refining process. Here we have vacuum facility as well as we have facility to push push oxygen. So, oxygen is going to decarburize, that means oxygen will react with carbon for decarburization. So, VOD uses vacuum as well as oxygen ingress to control decarburization. Then there is an RH process, is known as Ruhr-Stahl-Heraus degasser. It was developed in Germany. Ruhr is a very important area, industrial area of Germany. Stahl is the German name of steel. In German, in Deutsch language, steel is known as Stahl. So, this process, Ruhr-Stahl-Heraus degasser, This was developed and patented in Germany. So, this RH process is also a very important degassing process. Then another important is injection metallurgy. I have told you that sometimes it is necessary to control the inclusion shape, the inclusion melting point through injection of wet injection of Ca or Ca, calcium silicide or calcium iron. So, it is done through injection metallurgy. So, injection metallurgy is another secondary refining process. So, I have talked about LF, IGP, VD, VAD, VOD, RH, IM. There are several other secondary refining processes, but these are very common. That is why I want to highlight these processes. Now, earlier one I have told what are the desirable functions: deoxidation, carburization or decarburization, desulfurization, control of nitrogen hydrogen, that is degassing, then injection of Ca or Ca, then control of liquid still temperature. And then I have talked about what are the secondary refining processes. Now, let me show to you that which process is capable of doing which function. In one transparency, I am trying to show, I am trying to highlight what are the capability of the different secondary refining processes. At the left, if you look at the this transparency, you will find, or look at this slide, you will find first requirement is deoxidation, as I have told you. Now, what are the different processes which can do deoxidation? All these secondary refining processes can do deoxidation because this is the most important and fundamental requirement during secondary refining. Oxygen in liquid steel has to be brought down. So, deoxidation is essential, and all degassing, rather all secondary refining processes, whether it is VD, vacuum degassing, whether it is VAD, whether it is LF, whether it is VOD, whether it is injection metallurgy, whether it is inert gas purging, all processes are capable of doing deoxidation. Next comes desulfurization. Now, what are the processes which can do desulfurization? Again, we will find most of these processes are capable of doing desulfurization. VD, yes. VAD, yes. LF, yes. VOD, yes. Injection metallurgy, of course, yes, because you are putting calcium. Calcium can do a lot of good desulfurization. IGP, inert gas purging, you can do a minor amount of desulfurization, provided you can add some calcium oxide in the process. It is possible to get some amount of desulfurization. So, again you have found that oxygen control and sulfur control are two most important functions of secondary refining, and most of the secondary refining processes are capable of doing these two functions. Next, let us come to decarburization. Now, you will see that basically decarburization can be done only by VOD. VOD is, as I have talked to you, vacuum oxygen decarburization. The details I will come to later, how it is done. You are putting oxygen that will react with carbon in steel, and finally carbon monoxide will form, and this will come out of the steel. So, the vacuum will enhance this decarburization process. So, VOD is capable of doing decarburization. Now, I have told you that sometimes it is required to increase the liquid still temperature. That means, some heating facility is sometimes required during the process of secondary refining. Now, let us see which secondary refining processes are capable of heating the liquid steel. As I have talked to you, the VD is basically vacuum degassing, it has no heating facility. So, it cannot do any heating. VAD, vacuum arc degassing, that means there is a possibility of arcing, that there is a facility of arcing in this process. So, heating is possible. LF, ladle furnace, again this is possible because you have some arcing facility in this process as well. VOD, heating has to be done, there is no arcing facility, but through chemical heating. That means you can add some aluminum here, and you know aluminum to alumina reaction, that means aluminum reacting with oxygen to get alumina. This is a highly exothermic reaction. So, it is called chemical heating. In this process some heating is possible. Injection metallurgy, there is no heating facility. Inert gas purging, IGP, in the ladle again it does not have any heating facility. So, heating facility is possible in VAD, in LF. Basically these are two processes where there is a possibility of arcing, and you can increase the temperature whenever there is a necessity. So, we should remember that for all other processes, whatever liquid steel temperature is there, we have to live with it. That means there is no possibility of increase the temperature. So, the temperature management becomes a bit critical in all other stages, but except in VAD and LF, where there is a possibility of increasing the temperature, possibility of heating through arcing. So, it is easier to get a good amount of temperature management, better temperature management while you are using VAD and LF. Then let us come to degassing, that means control of the gaseous constituents in steel, gaseous elements in steel, which are hydrogen and nitrogen. So, what are the processes? Whenever there is a vacuum in the process, it is possible to do degassing. So, VD, vacuum degassing, it is possible. VAD, definitely it is possible. Then VOD, again there is vacuum, that means it is possible. LF, there is no vacuum in ladle furnace, it is not possible. Injection metallurgy, again no vacuum, so it is not possible. IGP, inert gas purging, there is no vacuum, so degassing is not possible. Only a minor extent of, because of you are pushing lot of inert gases, argon, so it might be possible to take out to certain extent, to small extent, the gaseous elements which are present in liquid steel, but it is a minor. So, basically there has to be a vacuum in the process. So, VD, VAD, VOD, these are the processes where you can do a lot of degassing. So, as I was talking of the different secondary refining processes and the capabilities, I was talking about inclusion modification, which is one important requirement. So, it is possible in VAD, it is possible in ladle furnace, possible in, of course, in injection metallurgy, because the whole purpose of injection metallurgy is to modify the inclusions. To some extent, to a minor extent is IGP, but not possible in VD, because there is no it is basically vacuum degassing, not much of possibility of inclusion modification, neither in VOD. So, I have talked about what are the different secondary refining processes, what are their capabilities.